It's great to be here. Good to see everybody virtually. This is a newish topic for me. We're thinking about how humans work with AI and how to design human AI interaction. And we'll talk about radiology. Uh, Please free to interrupt me for, if you have any questions. I'll take some breaks as well, but, if you raise your hands, I'll try to answer your question as well. And if I don't see your hand, then I'm sure one of the moderators will jump in and help me make sure that your questions are answered. So this is joint work with my colleague Tobias Salz, um, a grad student Alex Moehring at MIT, and a computer scientist at Harvard Medical School, Pranav Rajpurkar. Um, as Maynard said, this is a very important and current topic where we're thinking about AI, which is a transformative technology. Its general purpose and it's targeted at transforming at least high-skill tasks relative to previous technologies. So there are lots of concerns about what's going to happen to the workforce going forward. AI tools here have outperformed humans in a number of predictive domains. These include credit scoring, bail judgments, and medical diagnostics. And radiology is an iconic example in this space. It's characterized by this quote by Geoffrey Hinton, who's one of the founding fathers of modern AI, who said in 2016, "We should stop training radiologists now. It's completely obvious that within 5 years, deep learning is going to do better than radiologists." Now that prediction has not come to bear, but others have thought for a long time that instead of AI tools replacing radiologists, the more likely case is that radiologists who use AI will replace radiologists who don't. This is a quote by Curtis Langlois, who is a director of artificial intelligence and medical imaging at Stanford. And so the human in the loop is a common presumption in the medical profession for a number of reasons. This includes legal and regulatory hurdles, etc. But the idea really is that humans who know what they're doing will be able to correct mistakes that the AI has. And so today, what we're going to think about is whether human expertise and predictive AI are complements or substitutes. And if so, how should we design their interaction? Setting aside legal and regulatory barriers for now. Okay. As you start thinking about this as an economist, you'll start thinking about the comparative advantage of AI tools versus humans. So one of the things that humans have often access to is non-systematic information or data that cannot be coded up, systematically. So and cannot be used by AI tools as a result. So you can think about, your interactions with a doctor. It's hard to encode everything that the doctor learns about you as a patient. Radiologists don't interact with patients, but they have access to some kinds of medical information that the AI tools don't have because of HIPAA issues. But however, even though humans have access to this additional information, they might not combine sources of information effectively. And so they might not be Bayesians with correct beliefs about the joint distribution of their own information and the AI information. And so they might make mistakes. And then finally, an AI tool is costly to train, but once it is trained, it's very cheap to deploy. The marginal cost of deploying an AI tool is almost zero, whereas a human that has been a radiologist, for example, has to exert ongoing effort, and that can be relatively costly. So the question that we're going to ask today is whether contextual information in this context is valuable. Second, how do humans combine AI predictions with their own information? And third, how should we combine humans and AI in the system? So how should we design their collaboration? Okay, so what are we going to do? We're going to start with an information experiment with radiologists. We're going to have professional radiologists diagnose cases of potential chest pathologies. These are going to be retrospective cases, so we're not going to interfere with patient care on an ongoing basis. And there are two key features. First, we're going to vary the availability of AI assistance and contextual information. I'll tell you more specifics about exactly how the experiment works later. We're going to measure their diagnostic assessments and treatment follow-up recommendations. And we'll construct and compare the beliefs of the human radiologists relative to a Bayesian benchmark. And you'll find that they tend to neglect the automation a little bit. They don't seem to weigh the AI information as much as they should. And second, they tend to neglect the correlation between their own information and the AI information. And that those two types of mistakes result in a non-trivial um, delegation problem. And so the design will take the AI signal, let's call it SAI, and it's going to delegate the case either to the human, to the AI, or to a human that's assisted with the AI. And we'll think about both the time, the diagnostic quality, as well as the human time cost, assuming that the AI information is available always for free. The number of literatures that we are related to, we're building on a literature in computer science that thinks about human AI interaction, but the key difference is that it does not think about the behavioral economics of how humans process information and the biases that they might have. And so to do that, we'll build on work from Grether, for example, in behavioral economics to think about the types of biased belief updating that are prevalent. There's some work on human AI interaction in economics, but mostly they're thinking about performance. They're not thinking about the behavioral foundations of why human AI interaction does not achieve all of its potential. So I'm going to give you an outline of the talk and then pause if there are any questions. So we'll first describe the type of decision problems that we will think about in this paper. It's going to be narrower than all AI tools. AI tools are quite broad in nature. We'll describe the experimental design, provide you some results on the treatment effects, talk about the types of biased belief updating that we see, and then go to the optimal design of the optimal delegation solution. So I have a chat. I see. Okay, good. So this was just to, yeah, if you raise your hand and unmute yourself, I'm happy to take questions at this point if there are any. Okay, so sounds like I should go ahead. So let me describe the type of decision problem that we will be looking at. So we're going to think about a classification problem where there's a correct decision, omega, for case I, that could either be 0 or 1. It's a binary classification problem. There are prior probabilities pi of omega that the case should be classified as 0 or 1. There's an expert decision maker, R, who takes a binary action on case I. The binary action will be labeled AIR. It could be either 0 or 1. The payoff is going to be a standard classification type payoff. It's without loss to normalize the payoff of taking the correct decision to 0 in both states. And then if the correct decision was 0 and the expert decision maker recommended the binary action 1, then they're going to incur a cost of a false positive. If the expert decision maker recommended an action of 0 when the correct decision was 1, they're going to incur a cost of a false negative. There's a signal distribution, SE for expert, SA for AI, that's going to have some joint distribution given the true state of the world, the correct decision. And we're going to let these signals be arbitrary dimension. And so in this particular case, the heterogeneity is sort of limited, but we'll allow for it in the empirics. And so we'll estimate the cost of false positive and false negatives. So given that the expert observed some signal, which is a subset of SA and SE, the action that the expert R takes, depends on the odds ratio that the correct decision is 1 versus 0. Let P sub R of omega 1 versus 0 be the odds ratio of the expert's belief given the signal SIR that they observe. If that is higher than the relative cost of false positives to false negatives, then the expert would take the action 1 or would recommend the action 1. And so, the basic idea is that, if a missed case of pneumonia is much more costly than sending the patient home with some drugs that treat pneumonia, then even if the probability is not 50%, even if let's say the probability is 30% that the patient has pneumonia, the expert might recommend that pneumonia drugs are worthwhile. The belief P sub r might differ from pi, which is the true probability that the correct decision is one given the signals. So there are two key quantities of interest this framework points out. First is the relative cost of false negatives to false positives, CREL, that we'll estimate using recommended actions of the expert. And the second is the beliefs of the expert with and without AI assistance, okay, which we're going to elicit via the experiment. Okay. Now note that if you're a Bayesian decision maker with correct beliefs about the joint distribution of the signals and the correct decision, then you're always going to do better, weakly better, if you have more information. So if you see the AI signal. Okay. So now let's go through the experimental design a little bit. Okay. So the experimental design is going to be as follows. At the high level, what we're going to do is we're going to vary the availability of AI predictions and clinical history. So the first treatment dimension is access to AI, and the second treatment dimension is going to be access to clinical history. There is a third dimension in which we provide experts with additional incentives for accuracy. That arm did not have any discernible effects, and so I'm not going to talk about it in the presentation today. So incentives don't really matter here. We are hiring these radiologists to do a good job, and they seem to be exerting that type of effort. Radiologists in an experiment participate remotely through a tailor-made interface, which we designed. We designed this interface in collaboration with radiologists at Stanford Hospital and Mount Sinai Hospital in New York. This interface tries to mimic clinical practice as much as possible, with one key exception. We try to get structured, quantifiable information on their reports, as opposed to a text that would be hard to potentially parse ex post. We asked these experts, these radiologists, to diagnose one of 324 cases, historical cases from Stanford Health System. They provided with the chest X-ray in all cases, and then clinical history or AI could be provided depending on the treatment dimension. So here's an X-ray. This is somebody's chest, and they might have some disease, and so the expert can zoom in, zoom out, reset the X-ray, adjust contrast or brightness to try and help with the diagnosis. The treatment dimension one is an access to an AI algorithm. This algorithm was generated by Stanford University when one of my collaborators was there, based on a competition in which over 200,000 X-rays were provided, and a bunch of teams provided their algorithms to diagnose one of 14 chest pathologies. The collaborators at Stanford, they took some of the leading algorithms and they combined ideas from some of them to construct an algorithm called ChexNet, which is a large convolutional neural net. On the right-hand side of this slide, I'm showing you what you can think of as a production possibilities frontier that tells you the trade-off for the algorithm between the false positive rate and the true positive rate. So if you diagnose all the cases positive, your false positive rate is 1 and your true positive rate is 1. If you diagnose none of the cases positive, it's 0 and 0. And so if you can achieve a high true positive rate for a given false positive rate, your algorithm is doing better. So this is the production possibilities frontier between the false positive and true positive rate of the algorithm for a particular chest pathology. And then we've got 3 radiologists in the 3 different colors that show the performance of particular Stanford radiologists, and the algorithm is doing better than those radiologists. So in the treatment arm where we provide the AI assistance to the algorithm, to the radiologists in our experiment, they provided the predictions of 14 pathologies from this algorithm. This algorithm was trained to try and predict the labels that Stanford radiologists had in the past provided on these 200,000 plus cases. So these The text reports were extracted. The NLP and an NLP algorithm extracted the labels from these reports, and the algorithm is trying to extract predict those labels. So Arda, you have a question?
Yeah, so I was just wondering, so the participants in the experiment, do they see this AI diagnosis before or after they see the X-rays themselves? Do you know that?
Yeah. So we show them the X-ray and the algorithm at the same time.
Hmm.
The prediction from the algorithm at the same time, and they know that the algorithm only looks at the image and not at anything else.
Okay.
Yes, Dominic.
Um, I have another question. So what information do the radiologists get about the AI? Do they know something about the historical accuracy? Do they know something about like the certainty that the AI has in its predictions?
Yes. So we tell them about how it was trained, specifically that it was trained on 200,000 plus X-rays. We show them, these graphs. We tell them about the study, and we tell them the probability that the algorithm thinks that the particular case is positive, which is a measure of how sure it is that the case is positive or negative.
Okay, thank you.
You'll see that in a second, exactly how they're shown, the output from the algorithm. Great. Appreciate those questions. Okay, and then in addition to the X-ray, if they might receive clinical history, here's an example of it. So here's a note from the treating physician on the top right, 30 years of age, female, history of hypertension, abnormal EKG. Evaluate for cardiomegaly or mediastinal widening. So cardiomegaly means enlarged heart. And this is going to be important. The only way really to know whether somebody has an enlarged heart is through some kind of medical imaging technique or through an autopsy. Okay, and so that's going to help us think about what the correct decision is going to be. How are we going to classify that in a minute? Here's the interface that we use to elicit their assessments and diagnostic recommendations. So here you can see an airspace opacity where the algorithm tells that where the radiologist is informed that the AI prediction is 12%, which is very unlikely. Okay, so they'll see this bar. Okay, and they can use the slider to tell us about their own assessment. Here's a probability of 43%, but we allow the algorithm to we analyze the data, taking this 43% as a number, as well as taking it as ordinal, where higher numbers mean more likely and lower numbers mean less likely, because what if they're not calibrated, perhaps? Okay. And then the whole experiment is pre-registered, where we have all pathologies with the AI predictions, top-level pathology with the AI predictions. That's the group that we're going to look at today. And then overall abnormal normal assessment. Okay. All right. So what is this omega I? What is the correct decision? So we're going to construct a diagnostic standard omega I using the aggregate assessment of experts with lots of experience. So we had 5 board certified chest radiologists with at least 10 years of experience from Mount Sinai Hospital, which is one of the premier hospitals in the United States. And we aggregate their opinions to figure out what is the diagnostic standard for a particular case. And we're doing this because a definitive test is typically unavailable in the case of medical imaging for most part. Why is that? Well, the reason for that is that, if you think about this cardiomegaly example, the only way to really know whether somebody is cardiomegaly for sure is to do an autopsy. Okay, the other case is to have some kind of medical imaging or ultrasound, EKG or something like that. But these will all have the same type of issue, where you won't be able to measure the size of someone's heart exactly. It's only through imaging techniques. And so the correct decision will be based on what the aggregate assessment of these Mount Sinai Hospital physicians think. Okay. We're going to use a baseline cutoff of their aggregate assessment 0.5. We're going to do robustness to a number of variations. One is going to be robustness to log odds averaging as opposed to simple averaging. We've done versions in which we've dropped cases where there's substantial disagreement, so we cannot confidently rule out that this group of radiologists from Mount Sinai are unsure about what the correct assessment is. And so our results are going to be robust to a number of these variations. So radiologists tend to be a pretty good set of experimental subjects in many ways. First, remote work in their case is common. So this experiment we started during COVID. And so because of remote work, they don't have that much interaction with patients, which means that we can control the information environment pretty well. Okay, and we can mimic their typical workflow very well as well. We hired teleradiologists by contracting with 3 different companies on a spot market. They received a piece rate of about $10 per case that they read, and each radiologist read about 60 to 240 cases, depending on the treatment arm. And I'll tell you more specifics about how the treatment arms work in a minute. We trained them by showing them instructional video, explanation of how the AI tool works, comprehension questions, including the fact that the AI only uses the image. And there are several examples that we provide with AI prediction and burn-in practice cases to make sure that they understand exactly how the thing works, and then the initial cases are not particularly biased in any way. So there are 227 radiologists who participate in our experiment, who read on average about just under 100 cases. And so all in all, this experiment was about $250,000 total. Okay, so there are going to be some challenges in thinking about how exactly to design this experiment. Part of the challenge is that the experimental pool is expensive. The subject pool is expensive. And so in order to maximize power, we want to make sure we control for heterogeneity very cleverly. Second, I don't want to just compare the algorithms with performance to the human performance and vice versa. I want to go beyond that. Specifically, I want to construct a Bayesian benchmark and compare how our radiologists do relative to that Bayesian benchmark with correct beliefs. Okay, so if I take a look at the if I take a look at this expression on the right-hand side, the second term is the odds ratio of the correct decision being 1 versus 0 if only the expert's information is available. This is elicited from the experiment. Okay. Then once the expert also sees the AI assessment, there's an update. There's a likelihood ratio of the AI assessment conditional on the expert's information and the correct decision that gives you the posterior odds ratio. Now, I want to construct this posterior odds ratio by looking at the expert's assessment without AI, and then also find some way of constructing this first term on the right-hand side. Okay, I'll tell you exactly how that's done later, but let's say I could construct that term. Then I would be able to know what the correct update rule would be. And then I would like to elicit the human's assessment with AI again and compare it to this term on the left-hand side. And so in order to do this, the ideal environment, the ideal thing to do is to have a linked assessment within a radiologist's case, because radiologists are heterogeneous in their beliefs and the distribution of signals. Okay, so I'd like to elicit the beliefs with and without AI assessment, but that's kind of difficult, right? If I give you the AI assessment first, then you have to forget the AI assessment later on, and that may not happen. Okay, if I give you the AI assessment second, then there might be some order effect. So I want to control for these two things when I'm constructing this benchmark and doing so. So that's going to create some subtleties in exactly how I generate the experimental data. So let me go into that a little bit. Okay, so the first design, which is a relatively straightforward design, works like this. Radiologists enter our experiment, and they're randomized into 1 of 24 tracts, which is simply a permutation of the order in which they are exposed to the different information environments. So the first information, so for example, if you're on track 1, you'll see a set of images, say 15 images, in the X-ray only environment. Then you'll see a different set of 15 images in the clinical history environment. So that's X-ray plus clinical history. Then you'll see a third set of 15 cases in the AI only environment. Okay, so X-ray plus AI. And then finally, AI plus CH in set 4. So the radiologist is not seeing the same image in any 2 different information environments in this simple track. Okay, but what we have here is a within subject comparison where the same subject is seeing a different set of cases but in a different environment. So what we've done is we've controlled for the skill of the radiologist very precisely in this within subject comparison. Now you might worry about order effects that sometimes you see clinical history second or AI, and so that might create experimental demand effects or other things like that. And so what we have done as a result of this initial randomization is supposed to take care of that. So the first information environment that you encounter is randomized, equal chances of being X-ray only, clinical history, AI, or AI plus CH. And so that is a pure across subject design, and we can show that the treatment effects are not statistically different. Okay, now within subject design is going to be better powered. Okay, so there are about 150 radiologists with 60 cases each in this design. This design is great for getting effects on how well radiologists perform, but it's not particularly well suited for estimating whether humans are deviating from Bayesian updating. And so design 2 is intended to deal with that. What design 2 has is it has a washout period to get a fresh read under a different information environment. Okay, so that's going to allow us also to construct a Bayesian benchmark. So a radiologist enters the experiment. They, for example, start with session 1. In session 1, they see 15 cases in each of the information environment in some order. Then what happens is that for about 2 weeks at least, in many cases 3 or 4 weeks, the experiment is paused. They come back for session 2, and in session 2, they go through the same information environments, but a different set of cases are read. So for example, if there was a case that was read in the X-ray only environment in session 1, that case might be read in the AI environment in session 2. And vice versa. A case that's read in the AI environment might be read in the X-ray environment only, or any such permutation. But each of these cases will be read in all 4 information environments. And so what that allows you to do is to construct a Bayesian benchmark, because you see the same radiologist read the same case twice, once with AI, once without AI. The order in which the AI is provided is randomized. So sometimes you see the AI first, sometimes you see the X-ray only first. And the 2-week washout period is intended to sort of erase their memory. And we can test this a little bit, because in some cases, you'll see X-ray only in the second session, but AI in the first session. So we can see whether there's an effect of the AI in those examples. And the answer is no. When AI is provided contemporaneously, there is an effect, but when X-ray is provided, but AI was provided previously, there's no effect of moving towards the AI. And then finally, we have a third design. You might want effects. And in a third design, there's weekly more information in every session. So if a case was diagnosed under AI previously, we might add clinical history, but we'll never ask the radiologist to read the same case again without AI. Yeah, that's the question, Dominic.
Regarding the with treatment differences, so I understood that in the session 2 there they had different images in each of the treatments, but they would always start with X-ray only, then AI, or is this also randomized?
Sorry, this is also randomized.
Okay.
This slide should not have. We should have changed the order in session 2.
Okay. Yeah. Thank you.
Okay. All right. Okay, it's a good time to pause for any questions about how the experiment works. Okay. Sounds like there aren't questions about how the experiment works. So let me move on to the treatment effects. So the first set of treatment effects I'm going to look at is the deviation from the correct decision of the ground, what I'm going to call ground truth. So this is the absolute value of the difference between the radiologist assessment and the correct decision. When AI is provided, the treatment effect is, oh, sorry, I skipped a slide by mistake, I think. Yeah, I want to show you this slide first. So the first slide that I want to show you is the performance of the human versus the AI tool. So on the left-hand side, I've got the graph with the root mean square error. On the right-hand side, I've got the area under the receiver operating characteristic curve. That's the area under that production possibilities frontier. In the root mean square error case, smaller numbers are better. And in the AUC case, higher numbers are better. The AUC for a random classifier is 0.5, and the AUC for a classifier that's perfect is 1. And so in both cases, you can see that the radiologists are not doing as well as the AI tools. Each dot here is a radiologist and radiologist pathology. And the AI tool is better than 3/4 or more of radiologists. So the radiologists could do better just by following the AI in this example. Okay. And so let's go through the treatment effects. I'm going to skip this slide because it's kind of pretty obvious once you look at the pictures of what was done. And so this is the deviation from the ground truth. Providing the AI assistance alone does not decrease the deviation from the ground truth. This is something that you would think that Bayesians with correct beliefs would be on the negative side of this graph because they get weekly more information. And I just showed you that AI assistance is valuable because it's better than most of the radiologists. Okay, if you provide clinical history, the radiologists do a bit better, and the deviation from the ground truth falls by about a percentage point. And the interaction effect is 0 between clinical history and AI information. So you might think that the radiologists are not using the AI tool. That's not true. If I look at the deviation from the AI's prediction, that falls when the AI is provided. Okay, so by about 4 percentage points. So the radiologists are moving their assessments towards the AI tool, but they're not doing so in a way that's optimal, because otherwise their deviations would have been lower from the ground truth. So what's going on? Well, there's some heterogeneous treatment effects. So here what I've got is I've got the deviation from the ground truth split into different bins of AI prediction, either 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, and so on. If the AI is quite confident that the case is negative, or puts a very low probability that the case is positive, so provides an assessment between 0 and 0.2, the deviation from the ground truth falls. Okay, so the radiologists are doing better in that case. If the AI provides a middling signal, 0.2 to 0.6, well, the radiologists seem to err because the deviation from the ground truth increases, which wouldn't happen if they were Bayesians with correct beliefs. And on the extreme right, when the AI thinks that the case is positive, the confidence bands are large. And part of the reason why the confidence bands are large is that there's relatively less data in those regions. Most of the cases are in the left side. The average AI prediction is about 0.23. Okay, so there's some heterogeneous effect which shows that the uncertain AI is worse than providing an AI tool that is, or not providing an AI tool. Okay, so providing uncertain predictions actually misleads the radiologists. This is not only in the predictions, it also influences the treatment and follow-up recommendation. The probability of an incorrect treatment or follow-up recommendation is higher if the AI tool provides a prediction between 0.2 and 0.6. Okay, so my computer is freezing on me. Okay, so and then finally, let me show you the effects on the time taken. So this is a regression that tells you how does the active time, the number of clicks, etc., change when AI predictions are provided. You might think that the radiologists will become faster and they'll maybe take less time if the AI is provided. That's not true. The average time that the radiologists take without any additional information is about 2.5 minutes per case. And they take about 7 to 13 seconds, depending on whether you look at the first half or the second half of the images, when the AI tool is provided. So the AI tool makes these radiologists a little bit slower and does not necessarily help them. Okay. Let me go through now the models of biased belief updating that we will think about and how we go about estimating that model. So we're going to build on a set of models by Grether. This is a class of models. It's not the only class of models that you could think about. In this class of models, what I've got on the extreme right is the own information log odds. If you add this together with the prior, that term tells you the probability that the case is 1 versus 0 given the expert signal SE. And then I've got the likelihood update term from before, where this tells you how much the human should update in response to the AI signal. In the case where B was equal to D was equal to 1, this is the same as Bayesian updating. So I'm going to allow for cases where the humans deviate by not setting B equals to D equal 1. And we'll say that the humans exhibit automation bias if B is larger than D. The empirically relevant case is D is equal to 1. And we'll say that the humans exhibit automation neglect if B is less than D. Okay. We'll also allow for this other thing called signal dependence neglect. So the radiologists are told that so the AI tool can see the image, uses only the image in order to come up with this diagnosis. But the radiologist might not be correctly accounting for that correlation in their own information and the AI's information. And so what we'll allow for is for the update term or class of models in which the update term does not include SE. Okay, so in that case, they treat it as if the AI signal and their own signal is independent, conditional on the correct decision, conditional on omega. Okay, and so we'll run these two different models, and we'll see which model fits the data better. So in the paper, there's some theoretical analysis that I don't have time to get into. And this analysis shows that providing AI information will always improve performance if only automation neglect is at play. So if the update term is correct, the update from the AI is correctly thought through, so they think about the correlation correctly, but they just underweight the AI, then AI information in this model is going to weakly improve decisions. Why is that? Well, the humans are going to update towards the correct likelihood ratio, but maybe not all the way if B is less than 1, because D is equal to 1, which is the empirically relevant case. Second, if you're outside that, if anything else is happening, perhaps there's automation, signal dependence neglect, in that case, the delegation problem turns out to be non-trivial. Okay, and so potential gains from human AI collaboration could be undercut by the imperfect use of AI information. So we'll estimate B and D, and we'll estimate in different models to select which of the models fits the data better, whether it's signal dependence neglect or not. And we've also done versions in which we're not imposing this this linear form and log odds, and the linear form does a pretty good job at approximating the data actually. Okay. So how do we estimate the model? Well, the term on the right-hand side is something that we've elicited. Okay, we remember the experiment in which the same case was read twice, once with and once without the AI. So for a given radiologist, we've essentially elicited this up to measurement error, which we'll talk about in a second. You also elicited P posterior odds with the AI. Okay, so the key challenge is constructing this term. And in the key challenge in that, because we observe the AI assessment, even if we don't provide it, the key challenge is controlling for the dependence that arises because of the radiologist's own signal. Okay, so first, I want to rewrite this term in terms of a binary model as opposed to conditional densities, and so that you can do using Bayes' rule. So finding the distribution of SA conditional on omega equals 1 versus SE is kind of challenging. And so if you just take Bayes' rule, it's like predicting omega as a function of the AI information and the expert signal and so on. Okay. In order to do that, I'm going to assume that in order to control for SE, I'm going to assume that SA and SE are independent, conditional on the correct decision, and pi, where pi is the probability that the radiologist reports when only their own information is provided. So if I think about the case where the signal SE is one-dimensional, and the belief that the radiologist has that the case is positive is increasing in that one-dimensional signal, then this assumption is true. Okay. Now SE could be high-dimensional. What we're saying is that the probabilities that the radiologist reports without AI assistance is sufficient control for the dependence between the AI information and the expert's information. Okay, and so we're going to take a random forest to predict omega given SE and control for that. Now, the same radiologist had the same case twice, once with and once without the AI, 2 weeks apart, right? Now, that should be a pretty good measure of SE, but there might be some measurement error because, radiologists might see the case a little bit differently. They might, be in a different mood. They might be tired, etc. And so that results in measurement error in this term. And what we will do is that we'll address it using instruments. So we'll have two sets of instruments. One set of instruments is going to be based on just the AI assessment, and the other one is going to be based on a leave one out mean of the assessments of other radiologists for the same case. Okay, so now using this, we're going to try to figure out how do radiologists actually use the AI information. So we're going to think about the case where radiologists might act as if they treat the AI signal and their own signal as independent given the given omega, or they might ignore information in other pathologies. And so there'll be that's going to result in different types of models, different versions of that equation. And what we can do is we can estimate each of those models and see which model has the fits the data the best in some way. Okay, and so they just correspond to different specifications of the update term. And so we'll select the model with the lowest violation of the moment conditions. So we take a given model, we estimate it, we get the error term epsilon, and then we say, okay, we look at the moments where the moments are any function of SA and SE, but here we'll just take the vector of probabilities of omega equals 1 given the various pieces of information. And then under the true model, it has to be the case that that expectation is 0. Okay, and so we can test different models in this way using the method by Andrews and Liu. And so here's what we find. So we've got 3 different models, column 1, column 2, and column 3. In column 1, we estimate a model in which there's no signal dependence, so the signals are considered as independent by the radiologist. There's no pathology dependence, so the radiologists are acting as if each of the pathologies are being diagnosed independently, and therefore there's no correct updating. Okay. In column 2, we allow for signal dependence neglect, we allow for the radiologist to think correctly about the signal dependence, but we omit pathology dependence. In column 3, we think about correct updating. So both dependence across pathology and dependence across signals, across the AI signal and their own signal are accounted for. So we can estimate the models, each of these 3 models. In all of the models, we find that D is close to 1 and B is significantly less than 1. Okay, so there's a lot of automation neglect that is being exhibited. But the automation neglect on its own is not going to be able to explain the mistakes that humans make. Because remember, I told you that if automation neglect is the only issue at play, then the humans would do weakly better at all AI signals. What we find is that the model that best fits the data, this is based on the MMSC BIC, which takes the J statistic of the model and modifies it for the number of moments that it can keep, that it cannot reject. So the number of moments that we're testing are exactly 13. So column 1 fails to reject any of those 13 moments. So that's the model that best fits the data because it does not reject any of the moments. Column 2 rejects one of the moments. It has a lower J statistic because one of the moments is being dropped, but the MMSC BIC penalizes it for it. A more negative number is better, okay? And so column 1 is what's accepted. So that suggests that there's signal dependence neglect and pathology dependence neglect. Or at the very least, if you think that column 2 is better, then there's pathology dependence neglect. So at any rate, the humans are not taking the AI assistance and combining it correctly with their own information, and therefore they're making mistakes. Okay, so let's take a look at what these models imply about the type of delegation that makes sense. So here's again a picture in which I'm looking at the deviation from the diagnostic standard, and the horizontal axis I've got the AI prediction bin, and in black dots I've got the human only, which is pure data. There's nothing that's modified via the model. Next on this, I've layered on top the human plus AI, which is also data. And what you can see is that the human plus AI does a bit better when the AI is quite confident. You've seen that before in a different way where I showed you the difference between the two and the standard errors, the standard error of the difference. Okay. Now, because these data points are correlated, these standard errors should not be like subtracted from each other. the test was the correct test when I showed you earlier. Okay, and then the human plus AI does worse in the 0.2 to 0.6 range. In the 0.6 to 0.8 range, the human plus AI does a little bit better, and the 0.8 to 0.8 to 1.0 range, the human plus AI does a little bit worse. What about the AI only? Well, the AI only does really well when it is the. Sorry, I think I skipped a slide. I'll go back a couple slides to show you something. What about the AI only? Well, when the AI puts a very low weight on the case being positive, then the AI does better than either the human only or the human plus AI. So that already is telling you that the human plus AI is not going to do as well as AI only when the AI is quite confident, and you might want to automate these cases. When the AI provides a uncertain signal, the AI is worse than human plus AI. Okay, so here you don't want to give the AI to the human, but also you don't want to. You just want to do human alone because the human does the best. Okay, when the case is quite certainly positive according to the AI, then the AI does best. Okay, so let me go back a second because I skipped a slide that was somewhat important. This slide shows you. Remember, I told you that I had estimated these models that of automation bias and automation neglect, and signal dependence neglect. Well, it turns out that using a model in which there is signal dependence neglect is quite important in explaining the treatment effects. So in the black dots, I've got the human plus AI data. This is the treatment effect of providing AI to humans. Okay. Then in the square boxes, I've got the Bayesian human who has a correct distribution of beliefs. In the correct distribution of beliefs, the Bayesian is going to do much better than the human, and that's exactly what you see. And the Bayesian model cannot explain these treatment effects. Okay. If I look at the estimated model under the true joint distribution, which shows only automation neglect, you get the down arrows, and those down arrows are all below the 0 mark. Okay, and so that model with the true joint distribution, which only features automation neglect, cannot explain the data either. So what you need to do is to have signal dependence neglect. Once you have signal dependence neglect, what you see is that in the middling ranges, the human plus AI predicted by the model is worse than human only. And that mimics the treatment effect. It does not quantitatively get to all the way to this dot, but it shows you that that type of error is necessary. So that tells you already that human plus AI is not always going to be better because of this mistake. And so this graph was going to give you a hint of the optimal delegation solution, showing you that when the AI is very confident that the case is positive or negative, then automation is the best solution. And in the middle, the AI is doing pretty poorly, but providing AI assistance to the human is going to do worse. Okay, I'm going to pause again to see if there are any questions before I move on to the optimal delegation section. I'm doing pretty well on time, so it's fine if you guys have some questions, and I'm happy to answer them right now. Okay, I guess I'll move on. So given this, what we want to now learn about is how best to combine human AI, human assistance with AI, human effort with AI assistance. So what we're going to look at is a space of problems in which the AI signal is available for free, and then it can be delegated into either full automation, so the AI makes a treatment decision without any further intervention. There's no AI, so the human that works on their own, or there's AI assistance where the human is given the AI information and they make the diagnosis. So we're going to try to minimize the following objective function. Okay, the following loss function. On the right-hand side is the second term on the right-hand side is the effort cost. So we know the amount of time that humans take with and without AI for each of the signal distributions. And then we know the wage rate because we know that radiologists take about 2.5 minutes per case, and we pay them about $10 a case, so it's $4 a minute. Okay, so that tells us what the effort cost is. And then we know, what the humans, we know from the data, we're just going to work with the data now, what the prediction is under various information environments. So we know the probability with AI, without AI, and human only. We can convert that into a decision by looking also at the data, the treatment follow-up recommendation. And the treatment follow-up recommendation, using a binary choice model, allows us to convert it into relative cost of false positive and false negative. Okay, so that tells us what the decision is, and it tells us what the decision loss is in units of false negatives. Okay, so missed cases of pneumonia. And then we're going to have a parameter M, which we don't know, that converts decision losses into dollars. We find that the relative cost of false positives, false negatives is about 3.9 on average. Okay, so the humans are quite conservative. Even if the probability is fairly low, they're going to diagnose the case as positive. Okay, so what does the delegation solution look like? Okay, well, for very low costs of social costs of false negatives, all the cases should be given to the human. Okay, so that's all cases are given to AI. On the left-hand side graph, I've got I'm estimating this model using the Bayesian updated beliefs. So because I've estimated the conditional distribution of the AI signal given the human's information and omega. As the cost of false negatives increases, humans come into the loop. The time cost that humans take is, the additional time cost that humans take is relatively small. So there's very little case to make for human only if they're Bayesians with correct beliefs. And so at about social cost of false negative, about $1,000 per missed case of pneumonia, for example, about half of the cases should have human plus AI. Whenever humans involved with human plus AI in this example is better because we're looking at Bayesians. What about our subjects? Well, our subjects are making mistakes. So if I just look at the data, then as the cost of false negatives increases, humans start getting involved. But when they are involved, it's human only. It's very rare that human plus AI is being used. And that's because humans make mistakes when they're provided with AI assistance. So the upshot of this is that humans are more likely to work alongside AI than with AI. Now, you might look at this graph and say there are two other solutions, okay, aside from the delegation solution. One solution is that humans get trained, and I'm totally in favor of that. If you can find a way for these mistakes to be corrected, we'll be more in the left graph, but it's not trivial how to correct these mistakes. And the second thing that you might say is that, okay, what if I got the human's assessment beforehand and then combined it ex post in the correct way? That's also fine. You'd worry a little bit about strategic reporting by humans. And so I'm ready to conclude. We studied human AI interaction in radiology, and we found that humans exhibit two types of biases. The first is automation neglect, which does not necessarily on its own lower average diagnostic quality, but it turns out that human subjects seem to treat AI as independent, and that's potentially causing them to make mistakes. In particular, it seems to suggest that AI can hurt when it provides an uncertain signal. It also increases the time spent, and as a result, in the optimal delegation solution, AI assistance to humans is rarely optimal. And so I want to zoom out a bit and say that, although economists don't necessarily have comparative advantage in developing AI tools, they do have a comparative advantage in thinking about how humans use these tools, how behavioral biases affect this, and potentially organizational incentives that could be important in thinking about how to deploy them in the real world. Thank you. Appreciate your questions. I have a couple more minutes. If there are any other questions, I'm happy to take them at this point, but appreciate you inviting me to this seminar.
Yes, thank you for the super interesting talk. At the very beginning of your talk, you said that it is unlikely, or that you feel it is unlikely that AI might replace radiologists, but rather that the radiologists might be replaced by radiologists using AI. So in a sense, it is more about using not substitution, but rather different skills probably. So, and I was wondering, in your design now, you are more looking at the substitution case again. So where the radiologist gets information from the AI that is in essence the same task that he would also fulfill. So probability for the case description. So I was wondering if you thought about having like complementary effects, more in a sense that, for example, the AI would not provide a case description, but rather mark an area on the radiologist's image where it has some kind of I don't know, where it identifies some area of interest probably, and then the radiologist would provide the final diagnosis for the case. So, and so what my question comes back is, isn't that another case of substitution here rather than some kind of combined human AI knowledge that you spoke in the
So
beginning?
couple things about that. So first, that was a hypothesis. And just to be clear, AI tools come in all kinds of shapes and sizes. This is a predictive AI tool, right? And so when we talked about the decision problems, I looked at specifically predictive AI tools. And so in predictive AI tools, this is how I think about this. Here we are seeing substitution on particular cases, but it could be that there are complements in the overall production function because some cases can go to AI and some cases can go to humans, right? Then it's possible that the production process is the net production function that comes out of that is actually one that exhibits complements rather than substitutes. In the case that you suggested, where it's a particular region is highlighted, that's actually quite a difficult problem from an AI perspective. It's not obvious that problem is easy to solve. There are saliency maps, but there are issues with them as well. But that also, I would think about it in a somewhat similar way, because that's a signal SA that the AI is providing to the human. Now, that signal is not as easy to quantify and work with in empirically as compared to our signals, right? Because ours are probabilities. But actually, conceptually, it looks very, very similar. Okay, it's not conceptually a different thing. Here, AI and humans could have been complements, and the reason they could have been complements is that if I look at the Bayesian case, well, they turn out to be complements, right? Because if you're combining the information correctly, then AI is good at the image and knows what information to extract from the image. It does not necessarily know what the clinical history is because it can't see it. If the humans were good at combining these two sources of information, then we would have resulted in complements. So it wasn't quite the case that the research design or the setting precluded complements from occurring. It just so happens empirically we found that they were substitutes rather than complements.
Yeah, thank you very much.
Great, thanks for the questions. Happy to take other questions. If you didn't get a chance to ask a question, please feel free to write to me. My email address is on the screen. I'd be happy to respond on email.